Hello everyone. We're going to start with part 2 of our math review for AP1 Physics. And today we're going to talk about scientific notation and also a little bit about significant figures, but scientific notation first. Now you may have learned this part already in math, but we do it slightly differently in physics, so pay attention to this one. Scientific notation is how we represent numbers in a form that we can grasp. It's a way to put huge or very tiny numbers onto a paper in a relatively compact way, get rid of a whole bunch of superfluous zeros, and put it in a form that we can get our minds around. So, for example, if we have 4.78 times 10 to the third meters, this is an example of scientific notation. We have a root, that's the 4.78, and then we multiply it by some power of 10. Now, if we were to convert this into a regular number that was not in scientific notation, we would move the decimal place over 3 positions, and it would be 4,780 meters. You need to be able to convert numbers from non-scientific notation to regular scientific notation and back again. That's something you got to be able to do because we use a lot of scientific notation. And scientific notation pops up a lot in the calculations that you do. So if your calculator just spits out a big log number with lots of zeros on it or lots of decimal places in it, you have to be able to convert it to scientific notation. That's just a basic skill. Okay, here's another one. See if you can convert this. 92.1 times 10 to the 6 meters. What would that be in non-scientific notation? Okay, if you need to pause the video right now, do it, and then we will give you the answer in 3, 2, 1. Here we go. This is the answer. So 921,000,000 meters is what this comes to. So basically 92 million meters. And as you can see, 92.1 of something is easier for us to grasp than 921 and a bunch of zeros and who knows how many zeros there are. So that's why we do it. Takes less space on the page and is easier for us to understand. Now we can also go the other way with scientific notation. We can use it for very small numbers that are smaller than 1, like 0.0000765 newtons. That's a very tiny force. We could turn that into scientific notation by moving the decimal place, in this case over to the right, 1, 2, 3, 4, 5 places. And we get 7.65 times 10 to the minus 5th newtons. Super. This is how you learn how to do it in math, and it's completely proper. However, in physics, we do it slightly differently, physics and engineering. We like to have this exponent for the power of 10. We like that to be a multiple of 3. So, for example, in this case here, we had 7.65 times 10 to the minus 5th units. If we're going to make the exponent a multiple of 3, then we need to move the decimal place over one more position to make something times 10 to the minus 6. And it turns into this, 76.5 times 10 to the minus 6 newtons. Now, why do we do that? Well, it turns out that we have a prefix which represents 10 to the minus 6. This is 1/1,000,000th. And as you may recall from the other day, that is a micronewton. So 10 to the minus 6 newtons is a micronewton, and we have 76.5 of them. So if we're doing a calculation which is all in micronewtons, we can just use numbers between 1 and 1,000, and the math becomes fairly simple and straightforward, and we don't even have to mess with the exponents anymore. Now, if there's one thing that physicists are, it's lazy, and so are engineers. So this just saves us work and makes things simpler for us. And it allows us to use that relatively short list of prefixes which you saw in the last review video. Okay, that brings us to Sig Figs. Sig Figs, or significant figures, is something that you may not have run into before. But what significant figures are is digits in a number whose values are known with confidence. So the idea is if you're a researcher or you're doing a calculation, you have to report your answer using only numbers that you know are correct and get rid of the superfluous noise that's just kind of hanging on to the end of the calculation. Now, I'll give you a real world example. I actually saw this summer here. There was a short news report I saw about a near-Earth asteroid that had been discovered, which is going to pass within, the headline said, 18,641 miles of Earth in a few years. And I hope this jumps out at you as an oddly precise number. Because if these are truly significant figures, what the researcher is saying, is claiming, is that this asteroid 5 years from now, or whenever it's coming by, is going to be 18,641 miles away. Not 642, not 18,640, but 18,641 miles away from Earth. And that's absurd. So, how did this happen? Well, this is how it happened. The researcher reported that this asteroid is going to pass within about 30,000 kilometers of Earth. And the bot that wrote the article, or possibly a reporter, said, "Well, Americans don't like kilometers; they like miles. So I'll plug it into Google and get 18,641 miles, and that's how close the asteroid's going to be." Even though that's absurd. Um, this 30,000 is a rough number, so this number has to be rounded off some way. Now, how do we round it off? I'm going to show you the short version here, okay? When you get into college and take college physics, your professors and your TAs are going to be very concerned with you using the proper number of Sig Figs. It's part of our ethical responsibility in reporting scientific findings. Now, it turns out that College Board and AP isn't so concerned with Sig Figs. They just kind of don't pop up on the AP exam in the form that the tests are given, so they just kind of don't appear. But I do have a responsibility to you to expose you to Sig Figs so that you're not caught flat-footed when you go to college. So this is a shortened version of the rules for it. There's a lot more, but this will do for today, right? So how to manage Sig Figs. You complete your entire calculation. However many numbers you're throwing into the equation, you use all the numbers you've got to the level of precision that they're provided for. Or that you have, the level of precision that you have. And then once you have a final answer, then you round off your answer to the lowest number of sig figs that appeared in any of the numbers in the calculation. What? Okay, let me show you. So this number here, this 30,000 kilometers, is probably only one sig fig. He said it's closer to 30,000 than it is to 40,000 or 20,000. So the only digit that has meaning here is this 3. And all the zeros are just placeholders. So when we do our very precise conversion from kilometers to miles, now we finished our calculation, we have to round off this answer to a single sig fig, which would make this 20,000 miles, 2,000 miles from Earth. And that's reasonable. If the story said asteroid will pass within 20,000 miles of Earth a few years from now, and say, hey, well, okay, that's pretty good. And we all understand it's not exactly 20,000, it's about 20,000. But that's as precise as we can be given the information that the researcher provided to the newspaper. Now, one caveat here. Exact conversions have infinite sig figs. So if you're converting feet to inches, there are 12 inches in a foot, and it is exactly 12 inches in a foot. 12.00000 inches by definition. So that if the 12 inches in a foot doesn't mean that now you're stuck with only two sig figs, because it's 12.000. There's an infinite number of sig figs there. So that's not going to restrict your answer. That's that digit, that conversion, you don't take into account, or you don't consider when you convert to sig figs. So let's try an example here. How many weeks old are you? How many weeks old are you? And let's go with a typical student in the class, okay? And we'll say that a typical student in the class is 17 years old, okay? 17 years old. How many weeks old is that student? Okay, so he or she is 17 years times 365 days per year. That's how many days old, divided by 7 days per week equals 866.42857142857 weeks old. And the question is, now how do we need to round this off to the correct proper number of sig figs? Okay, so think about that for a moment. We'll count it down. 3, 2, 1. The correct answer is 2 sig figs. 17 years, that has only 2 significant digits. Now, we also use 365 days in a year, and that's 3 sig figs, but we're limited by the 17 years. Now, what about 7 days per week? Well, that's an exact conversion. So we're not stuck with one sig fig because 7 is a single digit. It is 7.00000 days per week. That's exact. So that doesn't restrict us. But we are stuck to 2 sig figs, which means 890 weeks is the answer that we can go with here. Okay, well, now what if you want to be a little more precise? What if our hypothetical student here says, hey, I was born in May. I'm not exactly 17. Today's not my birthday. My birthday's in May. And okay, so May, so we have June, July, August, September, 4 months beyond 17 years. So 4 months divided by 12 months is 0.333 years. Now, 4 months is also an approximate number, so we can really only use one digit of this. So that means that a student who was born in May is 17.3 years old. Now, it's more precise than the 17 years, but it's still not exact, 17.3 years. Now, what answer do we get when we use that number? So 17.3 years old times 365 days per year divided by 7 days per week. Now 902.0714285 weeks old. How much can we round this off to? In this case, pause it if you need to think a little bit more. But in this case, 902 is what we can go with. We can round it off to 3 figures because we have 3 significant figures in 17.3 years and 3 significant figures in 365 days per year. So we're okay going with 3 sig figs, which is 902 in this case. But what if we used a different method? What if we said 17.3 years times 52 weeks per year? Because everybody knows there's 52 weeks in a year. Oh, now we get 899.6, which rounds off to like 900. So what answer can we use? What's the right answer? Why do we get this discrepancy? Does this mean that one of these is wrong and one of these is right? Okay, well, think about this for just a moment. Okay, the answer is that both answers are completely correct within the constraints of the numbers we used. When we did that second calculation, we said 52 weeks per year. We said 17.3 years times 52 weeks per year. But is 52 weeks per year an exact number, or is it approximate? That 52 that we used is an approximation to only 2 significant figures. So this 900 weeks really is only 2 sig figs. And if we round off 902 weeks, a more precise answer, to 2 sig figs, it turns into 900. So these are actually the same answer. It's just we happen to have a little more precision with the 902. Okay, now last thing, we're wrapping it up here. What happens if we have a number 900 staring at us on the page? How many sig figs is that? And I'm not talking about the problem we just did. I'm talking about, hey, we see a 900 there. How many sig figs is that? Well, we can't tell. It might be that only the 9 is significant. It might be that, hey, it's exactly 900. Like, how many feet are there in 3 football fields between the goal lines? Exactly 900 feet, 3 sig figs. But we can't tell just by looking at this number. And if we use scientific notation, then we can tell. This is how we'd write it. If it was only one sig fig, where it was about 900 of something, closer to 900 than 1,000 or 800, then it's 9 times 10 to the second. It shows one sig fig. If it's 2 sig figs, 9.0 times 10 to the second. If it's all 3 sig figs, it's 9.00 times 10 to the second. And that's how we use it. So scientific notation is also useful for showing how many significant figures you have in a calculation. Okay, let's wrap it up here. Scientific notation uses a root times the power of 10. You learned that in your math class. In physics, though, we try to make the exponent on the power of 10 a multiple of 3. And the reason that we do that is so that we can use a relatively short list of prefixes so we can kind of do away with the powers of 10 entirely and just talk about nano units or kilo units or mega units. Sig figs indicate which digits have known values, and when you use scientific notation with sig figs, it removes the ambiguity from round numbers. So sig figs and scientific notation do do go together hand in hand. All right, thanks for your time. We will see you for the next one.